Yes, so I'm from Johns Hopkins. I'm from the lab of Dr. Kathleen Cullen, and I'm going to be presenting some preliminary results on a project which seeks to understand multisensory integration in primate vestibular cortex through ensemble analysis. And before I kind of jump into the meat of the talk, I just want to emphasize that this has been a collaborative project between the lab of my mentor, Kathy Cullen, and the lab of Dr. Adam Charles, who gave a great talk yesterday. And although I collected the data that I'll be showing you today, the modeling work was actually done by Dr. Charles' student, Noga Mudrik, who just couldn't be here today. So, in the Cullen lab, we are primarily interested in neural processing in the vestibular system, which, as you may be aware, is the sensory system that gives us a sense of head movement and position, more generally self-motion, like how you move through the world. And a really necessary part of this work is to understand how the vestibular system interacts with the proprioceptive system, which gives us a sense of joint movement and position. Because in everyday life, these systems are interacting all the time to not only coordinate and update head and body movement, but also to provide us with an ongoing sense or perception of head and body movement. And the interdependence of these systems is really obvious when we start looking at activity in various structures along the vestibular neuraxis. So previous studies from the Cullen lab have shown that most vestibular structures, including the vestibular nuclei, the vestibular cerebellum, and the ventral posterior thalamus, actually integrate both vestibular and proprioceptive input. And to date, most of our studies have been, actually all of our studies have been kind of constrained to these subcortical structures. And in my work, I am extending our exploration into cortex, specifically into this area called parieto-insular vestibular cortex, or PIVC. And this has been a really exciting project for me to jump in on, largely because relative to these subcortical structures and even relative to other cortical vestibular structures, we probably know the least about PIVC, but what we do know is that it receives both vestibular and proprioceptive input directly from the thalamus, which actually makes it unique among cortical vestibular structures. And also, the majority of neurons in this area respond to both vestibular and proprioceptive input. There are few unimodal cells. And that's actually sets it apart from a lot of other vestibular structures where you will find cells that respond only to the proprioceptive or only to the vestibular stimuli. But despite all this, we still don't really understand how this area integrates multiple streams of sensory input. And so to answer this question, I've been conducting high-density recordings in PIVC of behaving non-human primates using the NHP neuropixels electrodes. This has also been another really exciting part of the project because up until a couple of years ago, we were actually mostly based in tungsten recordings, and we made the transition to neuropixels like several years ago. So during these experiments, the primates are seated and are head fixed in a primate chair, which is then seated atop a turntable. In addition to the neural data, I'm also collecting kinematic data, specifically data about head movement and also about body movement via these two different sensors. And it's really critical for these types of experiments that we do actually have these two independent sensors, because a lot of our protocols rely on independently manipulating the head and the body to differentially activate the vestibular and proprioceptive systems. And this is really illustrated in my 3 experimental conditions that we're going to be exploring today. The first is a whole body yaw stimulus, so both the head and the body are moving at the same time, which means it's providing only vestibular input. The second stimulus consists of fixing the head and then rotating the body underneath the head, which activates neck proprioceptors and gives us a proprioceptive input. And then our last condition consists of passive head-on body rotations, which activates both the vestibular and proprioceptive systems. And I just kind of want to give you all an idea of the kind of data, the data characteristics that we're working with. So I'm currently recording from 2 adult rhesus macaques. In each session, I can extract between 50 and 130 single well-isolated units. Sometimes it's a lot more than that, but generally speaking, it falls between 50 and 130. In each condition, we have 20 transient rotations in each direction, to the left and then to the right. So there are essentially 20 trials in each condition in each direction. And then on average, these travels are lasting approximately, but not exactly, 1 second. And I just want to take a minute to look at the responses of individual PIVC neurons to our unimodal stimuli, to just kind of get a sense of their response properties. So these are 3 different neurons in response to this vestibular stimulus. And just looking at these, we can appreciate a couple of things right away. Namely that their peak times and also their peak amplitudes are quite varied across the neurons and also even across the different directions. So there's actually a lot of diversity even just within these couple of neurons. Now, this is the same set of neurons now in response to the proprioceptive stimulus, and we can see again that the peak times are varying in as far as like whether or not they're actually in phase with our stimulus. But also what we can appreciate going from the last slide to this slide is that not only is there variance between neurons, but there's also a lot of variance within neurons across different stimuli. And this is really, we can really appreciate this when we look at these neurons in aggregate. So these are heat maps just showing the average peak times for each neuron within a recording, well, in this case, within a single recording, to our vestibular and then to our proprioceptive stimulus. So you notice that these neurons are peaking at different times during the stimulus, which suggests that they're actually encoding different stimulus features. This is just a scatter plot of the sensitivity. So sensitivity is just kind of our estimation for the response magnitude of these neurons. So in response to vestibular sensitivity is plotted on the x-axis and proprioceptive sensitivity is plotted on the y-axis. And this is basically just to show you that there's a lot of diversity within these neurons as far as their responses. But these are just the unimodal stimuli, so this kind of brings us back to the actual question: how does PIVC integrate vestibular and proprioceptive input? So in our previous studies, in most vestibular structures, we have been able to estimate their response to the combined stimulus really well using just a linear summation model where we calculate the vector of each unimodal stimuli and then do a vector summation, and we get an estimate of the combined response. And as I said, in most of the other structures we've looked at, this has performed really well. However, when we apply the same analysis to PIVC, we find actually it's not estimating the response very well. In fact, actually, this linear summation is typically overestimating the sensitivity of these neurons to the combined stimulus. And so we could try other kinds of single unit analyses to further explore this, but given the diversity of PIVC neurons and the complexity of cortical dynamics, and now the fact that we have access to more data with NeuroPixels probes, we're probably more likely to achieve that fuller understanding by looking at population level activity. So there are a lot of really great methods for ensemble identification and also dimensionality reduction, a lot of which have been talked about here today. But unfortunately for us, they all had some constraints which didn't quite fit what we really wanted to do with this data set. What we really needed was a flexible, interpretable model to identify ensembles within PIVC. And we're proposing to do this with an updated version of a recently published model called Siblings. So Siblings stands for Similarity-Driven Building Block Inference using graphs across states. This is a graph-based dictionary learning approach, and it identifies ensembles along their temporal traces based on shared activation patterns across different trials and states. And so this is the main algorithm for Siblings, and just kind of to highlight that we're prioritizing data fidelity while also regularizing graph-driven sparsity and cross-state similarity. So Siblings has actually quite a few advantages for data sets like this, but the ones that I want to highlight right now are that it allows for overlapping ensemble membership within neurons, and then the membership magnitude can also vary across different states. And finally, it allows for non-uniformity of data structure, so it just gives us a lot of flexibility within this data set and other data sets. So in order to apply a model like Siblings to this data set, I have to define different states. In my case, these are going to be my experimental conditions. And each of these have a different combination of sensory system activations, which I kind of explained earlier. And then for the purposes of comparison within Siblings, we've also added this fourth null state. And this just consists of periods of time that are similar duration to the trials during the other conditions. But in these periods of time, the animal's not being moved at all, so it is still. Now, this is just a kind of visual representation of how Siblings is working. So it is modeling each trial via sparse state-specific matrix factorization, and the end result is that we get two different matrices. We have an A matrix, which captures essentially ensemble membership levels of each individual neuron, and then we also have our phi matrix, which captures the temporal traces of these potential ensembles. So looking first at the A matrices, this is just a snippet of one of our A matrices. So each individual column is a condition and each row is a neuron. And the color bar just represents that at darker colors, they have higher membership level, and then at lighter colors, they have lower or even negligible membership levels. So theoretically, if an ensemble we're looking at is capturing the activation of a particular sensory system, we expect neurons to have stable membership across conditions with similar system activation. And in this particular example, membership is most stable across conditions where the vestibular system is quote unquote on. So these are just kind of the full scale A matrices. The first matrix is actually just the full version of the one I showed you in the previous slide. So again, in this matrix, membership is most stable during conditions when the vestibular system is quote unquote on. And in the other matrix, A4, now membership is actually most stable in conditions when the proprioceptive system is quote unquote on. And if we look closely, we can actually see that there is a small amount of overlap between in ensemble membership between these two. So now that we have identified potential ensembles, we can start looking at their activity patterns, and this requires us to look at our other matrix, our phi matrix. And so we want to know whether or not how activity patterns differ with different system activations. So here I'm plotting the temporal trace for two different ensembles during the null condition. And perhaps unsurprisingly, there's not a lot going on there in the null condition. And this is in the vestibular only condition. And again, perhaps not surprisingly, there's more activity overall in this vestibular only condition. And within these two, or across these two ensembles, these temporal profiles are differing just slightly. So things get more interesting when we start comparing to our bimodal condition. So this is now, again, the ensemble traces for the vestibular only condition versus our combined condition. And so now we see that the ensemble temporal patterns have shifted slightly in that now in ensemble 7, the activity is higher during combined system activation, whereas in ensemble 8, activity is lower during combined system activation. And this is actually holding true across whenever we look at our other unimodal stimulus. So this is our proprioceptive versus combined. Again, in ensemble 7, the activation is higher, and in ensemble 8 it is generally lower. And when we kind of look at all of these together, we can appreciate that there are different kind of unique features or motifs across the unimodal and combined system activations, which points to some kind of multisensory integration that's happening at the ensemble level. But one of the things we want to know is, we have these quote unquote unique features / motifs, but are they actually meaningful? And so one of the ways we want to test, or we have been testing this, is by taking each ensemble trace and dividing it into 6 different time bins, and then taking the average activity during those time bins and feeding this into a logistic regression model, and then trying to figure out if we can tell what system is being activated based on the activity in each and every time bin. So this is a confusion matrix showing the results of, from one of our sessions, the results of the logistic regression model, and it's not perfect, but it's pretty darn good. So that just tells us that, yes, these activity patterns are encoding meaningful information about system activation. And so now also we can start, now that we know that these activation patterns are meaningful, we can start asking more interesting questions, such as, do particular time periods actually matter more for encoding than others? So this is a matrix that is showing each time bin for each individual ensemble, and also color-coded by their feature importance. And as we can see, feature importance is somewhat different across these ensembles. And again, this is for the vestibular-only condition. And actually now when we compare this to the vestibular-on condition, we see that the feature importance has actually shifted slightly in time for some of these ensembles, which is just kind of further evidence of some sort of multisensory integration that is happening during the combined condition. So this model continues to be updated and refined, and it's also being applied to other data sets. But so far, from these preliminary results, we have shown, well, first of all, we've shown that integration in PAVC is actually not really well explained by simple linear models. But through siblings, we were actually able to identify potential ensembles that differentially represent vestibular and proprioceptive activation. We also know how the ensemble structure varies across the different states. And then, exciting for me as the experimentalist who's working directly with the raw data, I really am interested in using these siblings identified ensembles in future analyses to understand multisensory integration in PIVC. So this is a similar scatter plot to what I showed you before, showing vestibular sensitivity versus proprioceptive sensitivity of neurons within a single session. And now I'm just overlaying some identified ensembles. And yeah, it's just an exciting possibility to be able to look at that and see how they're differentially activated in different analyses. So With that, I would really like to thank the Cullen Lab, in particular my mentor, Dr. Kathleen Cullen, and also the Charles Lab. Been fantastic collaborators, and I will try to take any questions. Thank you. Oh.
Very nice, Lex. Explain how the siblings decomposition is different from other sparse non-negative matrix factorizations that we put out.
Can you use your seat mic, please?
I am actually going to defer to Adam on this question because he probably knows a bit more about it than I do.
Yeah, so a couple. Okay, are we good? So there's a couple key features. So one thing is that it's not a single matrix factorization. It's more of a multi-matrix factorization. So each trial, while they share the ensemble structure, has different temporal structure. The other thing is that we allow that ensemble structure to change over the different conditions while being regularized to be not too different. And so that lets us capture how the ensemble structure modifies itself across the different conditions. And so that flexibility isn't really available in any of the other models.
Thanks.
Can you hear me? So the I like the decomposition into these different ensembles, and I'm curious if you can speculate about maybe what the sort of circuit mechanisms are that give rise to these different types of ensemble membership in different settings.
That's a really good question. I mean, so this area is totally different from other areas that we've looked at, just because, like, it has so many reciprocal connections with, not only thalamus, but also other cortical areas. And we have a lot of other kind of experimental conditions where we're maybe able to better tease that apart, but I haven't really dived super deep into that data yet, so maybe I'll have an update for you by SFN. Yes, over there.
Great talk. If you increase the velocity of rotation for one system and not the other, do you see something like a monotonic or non-monotonic increase in the delta between the neural activations for the two systems?
It's not as obvious here in Cortex as it would be in like a lower level structure where the encoding is a lot more clean. There is a slight difference, but yeah, there's a lot more going on in as far as like what's determining the response magnitudes and profiles, as opposed to just the velocity, although it is an important factor. Yes.
Is there a reason you expect it to be less clean? I don't know a ton about this system, but would you expect that cortical area would have a less, I'll just use the word clean because that was used, response than the vestibular input based on their overall function or like the architecture of that local circuit?
Yeah. So if we look at vestibular nuclei neurons and also like vestibular afferents, the encoding is just like so crisp, and it's largely because at that lower level where the system is kind of focusing more on like the fidelity of the signal, and then theoretically as it's going up the pipeline, it's getting transformed into something that could be used for something else like perception. So at lower levels, like a lot of, not all, but like a lot of vestibular signals are used in these kind of like reflex pathways, so you have to have really high data fidelity for that. But yeah, as you kind of go up the neuraxis, we expect it to be participating more in kind of perceptual stuff. So that's where we could kind of expect like the fidelity of the encoding to kind of like get a little messier. The thalamus actually surprisingly is relatively like quote unquote clean looking in comparison, which is also kind of fascinating. So it's more similar to the vestibular nuclei than it is to the activity in vestibular cortex. Yeah.
Thank you.
All right, well, if there are no more questions, I yield my time.
Thank you, Lex.